Hello, everyone. We are back with
Mhm.
another episode of Computer Vision Talks. And today we have with us Junyuan, and he's a PhD student at Michigan State University. And he was also a research intern at SonyAI. So we're going to discuss his paper, MECTA Memory Economic Continual Test Time Model Adaptation, which was accepted at ICLR 2023. And interestingly, this paper introduces a new problem and gives a solution to the problem they propose. And yeah, over to you, Junyuan. I'm really glad to host you today because probably this domain has very few papers so far, and we're expecting great work from you.
Okay. Uh, thank you for okay. Thank you for inviting me into this computer vision talk. So I'll start, right? Yeah.
Yeah,
Okay.
just ignore if you see people entering information.
Oh yeah. I think I already see that. Yeah. Okay. Everything good to go? Okay. My name is Junyuan. I'm a PhD candidate from Michigan State University. This is our work. How can we improve the memory efficiency in a continual test time model adaptation? This is a work done while I'm in an internship at SonyAI. So maybe let's start. Why do we care about this problem? So this motivation from like industrial scenarios when like say you have a self-driving car, you will use the models from a pre-trained model, which is like for example the Resident 100 from the PyTorch app. Then you want to download this model for recognized objects when you run a car on the road. But what will happen when you run an self-driving car on the road? You will encounter different values. Here is a very simple example. When you have different like fog, the night, the rainy day, or the snow day, all these different values actually this will make different data distributions. So we call this changing environments. So more generally speaking, these changing environments could mean different noise or different data distributions. Here we define this notion in terms of noise, and we want to make this model to be robust to this changing noise or changing environments. So here is a simple example. When you test the model on CIFAR-10, we will find that if we test the accuracy on clean samples, the accuracy will be quite high, as high as 94% for a CIFAR-10 pre-trained model. However, if you encounter like this changing environments or changing types of noise, you will find the accuracy drops significantly from 94% to 75%. So this is a big issue. That means the pre-trained model is not robust if you encounter different unseen noise at the test time. How can we address this? Recently, continual test time adaptation was proposed to address this challenge. This was proposed in 2022 called COTA or continual test time domain adaptation. In this problem, in this method they will first assume you can at the test time you will have a batch of unlabeled test samples which will be fed into the pre-trained model. Then the pre-trained model will use this unlabeled data to fine-tune the parameters. This is totally done in an unsupervised fine-tuning. Then after the fine-tuning, you will find that, oh, this is good. The robust accuracy increased a lot from like 57% to 87%. So this is what we want and how people done the continuous test adaptation. I want to give you more details about the continuous test adaptation. So assume that you have a batch of samples, say from rainy days, then you will feed these images into a pre-trained model. Traditionally you use this model to predict what the object is in this image. In these images, say this is a car in the confidence 90%. So for the test time adaptation, a very popular method is called tent, which will minimize the entropy of the model. Say this is a pre-trained model F seed, then we can compute the entropy per sample, and we will minimize the average entropy over the batch of samples. So this optimization is done in one step of gradient center for each batch data. Then when you have like a continually feeding batch data into the model, you will be able to continually update the model towards the different environments. So to when we look into the when we look into the model structure and check how this is updated, for the purpose of parameter efficiency, because at the test time you don't want to update all parameters or do this fine-tuning intensively. So therefore, very popular solution is that we only update the vectorization layers while we freeze all the convolutional layers to efficiently fine-tune these pre-trained models towards robustness against different test time noise. So this is the key idea, and this is core of this talk, that we only update the vectorization for the purpose of parameter efficiency. And we also have to mention that vectorization beyond all beyond statistics will be updated. The purpose of updating the vectorization statistics is to capture how the data diffusion shift. When you encounter different noise, this kind of noise will shift the feature distribution layer. Therefore, we have to update the statistics, which is the mean and the variance in the normalization layer, which will be updated by the new features. Therefore, it will renormalize the data to adapt it to new environments. So this is the two key strategies: only update the vectorization layers in terms of affine parameters, and update the statistics in order to capture the distributional shift. So also most recently in 2020 ICMR, there's one paper proposed to improve the sample efficiency such that less samples will be back-propagated and the computation complexity could be reduced significantly. So this strategy could make this algorithm more adaptable for like a new for the edge devices with limited computation resources. So these two methods is most famous in the domain of test-TimeAdaptation, which address the proposed first unsupervised adaptation strategy and propose how to make this computation to be efficient. However, there's a remain problem in this area. So let's get into the memory complexity of this algorithm. When we do inference, everything looks very good because we only for a resident 50, we only need about 800 megabytes or about 900 megabytes of memory to run this model to predict what the object is in an image. So this is pretty cool for HDS like a Raspberry Pi, which has 1 to 4 gigabyte RAM, which is totally enough for inference. However, when you want to do the continual test-TimeAdaptation, this memory is not enough anymore. Because we noticed that when you want to do the back-propagation, actually you need more memory because we want to compute the gradients, then you have to do some cache. The cache is stored when you do the forward, then which will be used to compute the gradient in the backward. So we notice this is a very large memory load, which is like a 4.5 gigabytes. Because of this high memory consumption, today's continuous adaptation cannot be adapted to a small device like a 4 gigabyte RAM Raspberry Pi. So this is an emerging question: how can we fit this continuous adaptation algorithms into low memory devices? How can we improve the memory efficiency?
I have a question. You talk about TENT and EATA here, not about COTA. Is COTA better at memory consumption?
No, actually, COTA is not efficient in terms of memory, and also it's not efficient in computation. So COTA is even more complicated because it will do the end-to-end updates. It will update all parameters, so it's kind of more inefficient. Yeah. So I only decided these two methods in my paper because they are more efficient by only updating vectorization layers, and we will compare compare the quota in our experiment, we show that this quota is totally not efficient. So that's why we will focus this too. Yeah.
Right. I read your table one, and in that one as
Mhm.
well, you were not reporting the numbers on quota. So that's why I wanted to ask the question.
Oh yeah, I compare in the table two. Actually, we
Yeah.
have a full benchmark to compare multiple baselines. So yeah, we will try to compare in a more standard settings. Yeah.
Thank you.
Mhm. Okay. Thank you for your question. Yeah. So let's go back to our problem. So we noticed that this is a very large memory node. So here's the question: where the cache comes from? Why do we have this large cache? Notice we already make this algorithm quite efficient by only updating the batch transition. Why this memory is still so large? So notice that when we say we are updating the batch transition, we are updating two things. One is the statistics, which is very lightweight. Another thing we want to update the affine parameters, which is like a low dimensional as the channel-wise parameters gamma and B. However, if you want to compute a gradient with respect to the gamma, then you have to simple calculation can show that you have to need two terms. One is the gradient back propagated from the deeper layers. This cannot be obtained before you do the back propagation. Therefore, meanwhile, you need another term we call cache. The cache is actually the feature maps input into the affine projection. This cache is actually the normalized features in the batch transition layer. So this matrix is pretty large, and it has to be stored in the memory before you can do the back propagation from the deeper layers. So this is why we call it cache. It has to stay in memory for a while until you finish the back propagation. So this is a very large matrix because it scales by the batch size, scales by the number of channels, also scales by the number of layers. Here we show this multiplication in terms of back propagation. Yeah, it will start from the first layer to the last layer. So in comparison, we already know that forward is very memory economic. However, in comparison, here we show that this is economic because you only need to store the cache for one layer. This is the term multiplied by batch size, channel size, and the image dimension. And this does not scale by the number of layers. So this is quite efficient if you want to do inference. However, in comparison, backward is not efficient. You have to store many data in order to do the backpropagation. So here we summarize that traditional continuous test-TimeAdaptation has a very big issue in the memory consumption. It cannot even fit into low memory devices, and especially for very large models. So the key reasons for the low memory frequency is because you require larger batch size. The larger batch size is essential for estimating the statistics like the mean and the variance in the normalization layer, and also it requires a very large layer and the channels, which will scale up the cache size. So in this talk, we will introduce a new algorithm called MECTA. That is a memory economic model adaptation solution. So from here, I will give more details. How can we address this problem from the three dimensions, like the batch size, channel size, and layer size? So given the notation that we already know that the cache is defined by the normalized features. So first step, we want to reduce the batch size. So in a high level, we want to it's quite trivial. Just feed fewer images into the network, you can reduce the batch size. But the problem is you may not get accurate statistics. Notice the statistics of mu or the mean. It depends on the number of samples in this batch. If you reduce the batch size, the estimation will be less accurate. Therefore, you will not have a good normalization because you have a bias from a small sample size. So the problem is how can we maintain a good accurate statistic estimation while we reduce the batch size. Secondly and thirdly, we will reduce the channels and reduce layers to update, because we don't want to compute so many gradients. But however, when you drop this cache, you will also drop the gradients. That means some layers will not be not updated. Some channels will not be updated. So this is a problem, because when you drop some gradients, you will lose some accuracy on updating. You will not be able to fast adapt to the new environment. So this is a problem we have to consider. So this is the high level of the MECTA that we will reduce the batch size, number of channels and layers. And the challenge is how can we reduce the memory complexity while we maintain a good accuracy of the statistics and the gradients. So first, we want to reduce the batch size, and we know that reducing the batch size will lower statistical accuracy. So say this is the statistics of we denote the statistics as the phi, which could be the mean and the variance. We combine them together. So this is the phi hat, which represents the statistics of the current batch data, which may be inaccurate if you reduce the batch size, as we mentioned before. So how can we address this? We leverage the idea from traditional batchization, like traditional batchization will compute a moving average of the statistics during the training, such that we can use this statistics at test time. But here, recently continual test-TimeAdaptation will only use the current batch statistics, and they totally ignore the training statistics and all the previous memory of the statistics from like previous batch. So here we reuse this memory in order to get a more stable and more accurate estimation of the mean and the variance when the current batch is small. So this is the key idea of to reducing the batch size when maintaining accurate statistics. However, this is not that trivial. Actually, this is not trivial. The challenge comes from the environment is changing. We have introduced a new parameter called beta here, which will trade off between the previous memory and the current batch statistics. So what's the best choice of beta if we are in a changing environment? So changing environment, we mean we have different data distribution. So we have different statistics during the test time. So if we simply set beta equals to 1, this will degrade to using the current batch. As we know, it's inaccurate. This is not what we want. Also, if we only set beta to equals to 0, this will be a problem, because we only use the previous memory, or we only use the training statistics, because the training is done on totally clean data, and this statistic is very inaccurate for the changing environment with different data distributions. We cannot use the statistics beta equals to 0. It's not a good idea. So therefore, in high level, we want a beta between the 0 and 1, which can perfectly trade off the accuracy and adaptivity, such that we can have a good estimation of the statistics when we can also quickly adapt the statistics to new and emerging environments. So how can we do that? Here's the intuition. First, we notice that if the distribution is stable, like say all the nodes are like the foggy, then we just we say this distribution from the last batch and the current batch are the same. So we say the environment is quite stable. In this case, intuitively we know that okay, for a stable environment, we may don't need to update the statistics, because it's like a constant. We don't need to update. In comparison, if the previous environment is different from distribution is different from current distribution, that means the environment is unchanged. We have to adjust our strategy to quickly adapt our statistics to the new environment. Therefore, we will prefer this beta to be closer to 1. So this is the high level when we should set a beta to be a smaller value, one we should set a beta to be a larger value. So so technically we will implement this by observing the fact that we can actually use the memory statistics and the current batch statistics to notice to see how this environment changes. Because since we cannot directly model the data distribution, but we can model the feature distribution per layer. So say if the previous statistics is totally same as the current statistics, or approximately similar as the current statistics, then we may want the beta to gradually vanishes to 0. Otherwise, we want to like beta gradually increase to 1, such that it can quickly adapt to new data distribution. So we have proposed a heuristic strategy that is beta will be defined by the similarity between the current statistics and the past statistics and the current statistics. So we measure the similarity between the two statistics by a symmetric Carroll divergence. So the Carroll divergence, in the Carroll divergence, we assume the two statistics will model Gaussian distribution. Of course, this is kind of an approximation of the feature distribution, but we notice this kind of approximation works pretty well in practice. So then we use an exponential term to reshape this distance into a range between 0 and 1. Then we plug in the beta into the moving average to dynamically adapt the statistics to new the memory previous memory. So this is the strategy of our reducing maximization. We use the moving average to stabilize the static estimation, and we use an adaptive parameter to adjust the to trade off the memory and the emerging statistic. So after reducing the batch size, we are interested in how can we also reduce other dimensions. Here I will decide how can we reduce the channels, which by reducing channels we mean we will drop some channels in the cache. So a trivial idea is like we just drop the like a q times 100% channels in cache. That is for cache metrics, we will drop elements in the specific channels. So we can randomly drop this. But however, we notice that when you drop these channels, you will not be able to compute the gradient in these channels again. So this means you will lose the ability to update some specific channels. So this is not a good idea because a good adaptation requires enough gradient information. So if dropping them, you will lose accuracy. So therefore, we propose another way. Instead of constantly dropping specific channels, we randomly drop some channels. That means we will introduce a random masking matrix which will randomly drop the channels in different batches. Say for the first batch, we will drop the first channel, and then in the second batch, we may drop the second channel. So in terms of because of the randomness, we can take the expectation over the masked cache. We will notice that this expectation can be restored to the original cache if you have enough batches. So this is a good idea by stochastically dropping some channels, which may drop some gradients in one batch, but it will finally recover a gradient after several batches. So this is but the benefit is that we can also reduce the memory. So another benefit of dropping some channels is that we can have some implicit greater regularization. So this is motivated by actually the problem raised by New in 2022. They show that the continual test-time adaptation leveraging the the tent or the interest in randomization will suffer from catastrophic forgetting. That means when you continue to adapt to new environments, you will lose the accuracy either on the clean samples or previously noise, and you will see the accuracy of the model will gradually vanish to the zero. So this is what we call the forgetting in continual test-time adaptation. So we can show that by using our stochastic gradient cache dropping, we actually drop the gradients, and then for the update time t will differ from will be upbounded by the gradient norm in each steps. And we know that if we drop a cache, we will drop the many elements in a gradient. Therefore, the norm of a gradient will be greatly reduced. Also, in the later experiments, we also observe that by using the stochastic dropping, channel dropping, we can greatly improve the TED from forgetting. That means we'll have a more stable accuracy during the continual updating of our models. So in addition to the batch and the channel reduction, we also introduced how can we dynamically address the number of layers we needed to be updated. So that means we may want to drop some layers, some caches of layers. So of course, similar as the dropping some channels in each layer, when we drop a cache of one layer, we will definitely drop the corresponding gradient. So this is also, as we mentioned, this is very bad because if you want to update the parameters, but this may not be less bad if the environment is stable. Say already this whole model and enter the constant environments, for example, the rainy day, then we may not always continue to update the parameters. So a good idea is like maybe you can stop the gradients or drop the cache to save the memory, because we don't need to update some stable layers. So with the intuition, the question should be when to stop the updating and when we need to restart. Obviously, we need to stop update the specific normalization layer if the environment is already stable. And if the environment changes, then we need to restart it in order to capture the distribution in the new noise and the new data, probably. So recall that we have, but how can we know that? How can we know the environment trends? So actually, recall that we already have some estimation in when we try to reduce the batch. We know that we can define the environment trends as the distribution similarity, like from the past memory and past distribution and the current distribution. If they are the same, then we say the environment is stable, otherwise it's unchanged. And we know this that we already have a parameter, already have a parameter beta to capture this kind of change. If the beta estimated by our heuristic algorithm is close to zero, then we say this environment is stable. Probably we need to stop the gradients in this layer. Otherwise, beta is close to 1. Then we probably will need to catch up the updates in the data distribution. We need to do some back-propagation in this layer. So therefore, this is a very straightforward solution here. We just stop the gradient if beta is smaller than some threshold. Otherwise, we will increase the we will restart the gradient in this layer if the beta is larger than threshold. So this is also a very simple idea. How can we dynamically determine if we need to compute gradients or store cache for a specific normalization layer? So in summary, we propose 3 strategies to reduce the memory consumption in the continuous time adaptation. We reduce the batch size while we can maintain a good accurate statistics just using very small batch size. Also, we introduce like a channel sparse gradients by stochastically prune some channels. If you have a lot of batches continually coming into the stream, you will be able to restore the actual gradients per layer. Also, we can dynamically determine when should we to compute a gradient and when for each layer and when should we stop it. So this strategy can maintain a good trade-off between memory and accuracy. Here we give an example highlight on the memory improvement. We show that compared to like a 4.5 gigabyte cache size in using the traditional CTA, our method can like significantly reduce the memory consumption from like about 5 gigabytes to like just 700 gigabytes using a small batch, using the stochastic dropped layer memory and the dynamically adapted adjusted layer memory. So how good is this method perform? We show that we compare our algorithm to several baselines. We show that our here we benchmark our algorithm in changing test time noise. We conduct experiment on the ImageNet. When we have like 15 types of noise, from the like general noise, from the blurry noise, or the weather noise, or the digital noise. This kind of noise was very standard in terms of the robustness evaluation, which was first proposed at Hendrick in 2019, where they evaluated the current SOTA models to show how robust this algorithm will, these models will be in different nodes. Here we sequentially feed the data with this noise into the models. We will first let the model go through the Gaussian noise, then the short noise, then impulse noise. Then we will summarize the accuracy on each noise. So this accuracy is actually computed on all samples on this test set with Gaussian noise. And then we sequentially evaluate all these nodes. And finally, we will compare the average accuracy on all these 15 nodes. And we show that our method actually have a comparable accuracy with related to the EATA baselines. And we noticed that EATA is the best algorithm that can greatly trade off efficiently fit adapt the model at the test time. Also, we compute the cache size. So by cache size, we mean we only accumulate the metrics cached for each patronization layer. So this may be a bit smaller than the actual memory size, but we want to focus the cache size, which is the biggest memory consumption in a network. We show that below this, although this EIK is claimed to be efficient in terms of computation, but it's not efficient in terms of memory. It consumes a lot of cache, like it's about 2.8 gigabyte in order to do the back-propagation. So similarly, quota and the tent consume a similar complexity, because if here we apply we assume the quota only update the patronization layers, because it's in the purpose of fair comparison. Actually, in the original quota, they may want to to do the end-to-end fine-tuning. Also, we also compare to several baseline algorithms from the previous literatures, including Memo. Memo required you to previous already seen some noise during training. Also, the fully test-TimeAdaptation using different normalization layers. And the BN is a very elegant, probably the first algorithm that proposed to only updating patronizations, such that it can adapt to new noise. And also we compare TTN. So BN is quite efficient, because these two algorithms is quite efficient because they have very lightweight update on the back-translation. For BN, they only update the statistics, so no back-propagations. Therefore, you don't need a lot of cache. So however, these two algorithms is so poor in terms of accuracy, because they cannot. This is because the updating on a finite parameter is essential to capture to gain a good accuracy on noisy samples. So merely updating the statistics is not enough. So in terms of accuracy, our method is pretty good, and in terms of cache size, our method is it's comparable. It's just a bit larger than batchization when they all use the same batch size, and our cache size is much smaller than the best accuracy algorithm EA. And even we apply some advanced technique called gradient checkpoint. Gradient checkpoint will not change accuracy, but it will reduce the memory consumption by feeding in some computation resources. So it only reduced the cache size by half, and it's still two times it's twice of our cache size. So therefore, we want to conclude that our algorithm provide the best trade-off if you using the same batch size. So this is the best trade-off between the memory and the accuracy. So in addition, we want to show that our improvement is not static, not a static constant. It's a dynamically changing. As we mentioned before, we have a layer adaptively memory usage. That means when we encounter a stable environment, we will gradually reduce the need for more cache memory because we don't need to update many layers. Instead, if we encounter a new environment, our estimation of the environment will peak the cache size in order to capture the difference in the new noise. And in comparison, even in the peak memory, our algorithm has much lower memory consumption compared to the EATA or EATA with the gradient checkpoint. So we also compare all these some main algorithms in terms of constraint cache. If we in this table we constrain the memory cache consumption by the batchization. Here we use the batchization with the 128, which is pretty large, which can capture very accurate statistics. And this memory is like a 411 at the max at the maximal. So we make sure every algorithm compared has a smaller cache size. Then we compare the accuracy here. So here's two things, two takeaways. First, our algorithm still has a very good accuracy because even in a constrained memory, and our algorithm has a very good computation capacity. It is only slightly larger than EATA, but it's gradient checkpoint will trade in a lot of computation capacity in order to get some saving on memory. And our algorithm is like a much accurate than baselines. Like it's about 5% of accuracy improvement. And our algorithm is accurate in all 15 kinds of noise on ImageNet dataset. And also as we mentioned before, stochastically dropping some cache can mitigate the forgetting. And here is the experiment result to show that for the 10 algorithm, it will suffer from catastrophic forgetting if you continually adapt the algorithm by 15 kind of nodes sequentially. So our algorithm, because we drop some caches, we will stop some gradient of layers. Our algorithm will greatly improve the accuracy in the later stage of the tent. This is much better than tent because we like mitigate the forgetting. So although this is still not good at EATA, EATA is known to be good at mitigating forgetting, but our algorithm it's not good at memory saving. So this is two key points. Our algorithm can mitigate forgetting and achieve a better accuracy under the constrained memory consumption. So also we are interested to ask how these three different components affect the memory consumption or affect the trade-off between memory in terms of cache size and the robust accuracy in terms of mean corruption accuracy. By mean corruption accuracy, we mean accuracy averaged on five types of noise. So we show that this trade-off our algorithm can gradually push forward the frontier of the trade-off until to be like very accurate and also consume very low cache size. So here let's do three steps. One step we improve with different smaller batch size while we maintain a good accuracy. Then we push forward with more with like strategies of reducing the channels and reducing the layers. In conclusion, we noticed that reducing the batch size and the channel size is more effective in improving the frontier. But dynamically reducing the layer is good. Actually, it's more useful when you only have a very small cache size. We may dynamically reduce the cache size to some at some time point. So in summary, in this work we introduced a new algorithm and new problem. In terms of problem, we revealed that current continuous time adaptation is not efficient in memory. You have to, if you want to adapt this algorithm to edge devices with limited memory, you have to improve the memory efficiency. Therefore, we propose the first algorithm, which only use a simple plug-in MECTA Norm that can certainly improve the memory efficiency with CTA algorithms. Also, we show this algorithm have a very good trade-off between the memory consumption and the robustness. So thank you very much for coming to this talk. And this is the QR code. You can find our paper and the code, source codes online.
Okay, that was a great talk. And you mostly answered all the questions that I was waiting to ask you
Okay.
as we move forward.
Yeah.
But first thing to get started with, why do you think the current CTA ignores memory efficiency? Is it an unavoidable trade-off with performance? But you say that it is not actually. You compared how accuracy could still be maintained with memory. But why do you think it is being ignored?
Yeah, I believe we will have two ways to show that this is traditional algorithm is not efficient in memory, because first we can measure the memory consumption. We may find that at least if you want to do a forward with like 64 batch size, you have to store a large cache size. So so the other way we can analyze this problem by the gradient. We show that if you want to store this computer this gradient, you have to store this feature map, which scales a lot by the batch size, the channels, and the layers. So I believe this is a significant issue for the continuous adaptation. Yeah.
And talking about batch size, have you tried it for like batch size one, sample by sample? How does MECTA Norm perform when you just have one?
Oh no, let's probably, but actually I don't think it's not that trivial. So if you only fit one sample into the today's network, it may not compute the batch size accurately. Especially it's very small, like just one. It requires some different algorithm. Definitely not the moving average. Let's some algorithm in the traditional in deep learning, like can use like one sample each time, but it will greatly reduce sacrifice accuracy. Yeah.
I see. And as we have been talking about just the batch norm layers, I was reading quota, and for their segmentation task, they switch to seg formers, or people are using vision transformers as well. So there you have layer norms. So would you be switching layer norms as well?
Actually not. Actually not. I think this is a big limitation of our work. We can only be adapted to like batch transition layers. But I think batch transition is very popular in traditional convolutional layer, convolutional networks. But so for the transformers, yeah, of course, in terms of transformers, quota is like a more general, and the 10 is should be works well. But I believe, but we already show that batch transition has some specific advantage in robustness. It can capture like statistical difference. And previously, people have shown that if you say like group norm, this kind of different normalization, do not have a very good accuracy compared to the EATA. this is the EIT, the result reported by EIT. They show that the personalization has a specific advantage in capturing the noise robustness. Yeah. So yeah, of course, I believe it's a very good idea to explore different normalization layers. And I believe there's one paper in this year's ICRR. They discussed the choice of normalization layer. You can find it online. They compare different normalization layers. So I believe in some specific conditions, group norm or layer normalization has their advantage. But in this paper, we want to focus on the back-translation because of the EIT and Tent adopt this normalization layer. Yeah.
Right. And one question I had is that because EATA filters out samples on the basis of entropy, like
Yeah.
um, and there are lesser number of samples that are being backpropagated, right? So that is why it could be more efficient memory-wise. But
Yeah.
performance,
Oh no. Yeah. Sorry,
uh,
I have to correct you. That's not more efficient in memory because you don't know which sample you want to backpropagate, right? Before you get a loss. Because EITA will use the loss to determine which one you want to backpropagate. So if you don't backpropagate, you will save the combination cost, but you will not save the memory cost because you have to cache all the memory before you know which one you want to backpropagate. So therefore, for even you are only backpropagate one sample, you have to cache for 164 samples in your batch. So that's why we say EITA do not reduce the cache size. Yeah.
I get it. Okay, that's interesting. And did you evaluate forgetting by any chance? Like after you had a model that had seen all these corruptions, how it was performing on the base data set?
Oh yeah, we evaluated. So in this table, actually, we include the accuracy on the original data set. In the last column, you will see that our methods will maintain a better accuracy on the clean samples. So we put it in the last as the last data set because we want to know after explaining so many different nodes, you adapt so many different nodes, how well you can still remember the knowledge on the original data. So interestingly, we find that this can still maintain very good accuracy. But I would say this is probably mostly because of the EAT has a very good ability to maintain or to mitigate the forgetting. For Tent do not have this ability to maintain accuracy on the past data set. So but notice that we have some strategy to mitigate the forgetting. Therefore, we still have improved a lot on the original dataset by using just the tenths of optimization algorithm. Yeah.
Okay. And the last question from my end is I'm asking this for Nikhil, who works for segmentation and domain generalization.
Mm.
Do you think this work is extendable to segmentation tasks?
I'm sorry, I'm not very familiar with the segmentation, but if there's any specialization, I believe this will be helpful. I believe it's a very interesting question. How can we? I have not seen many work on applying test-TimeAdaptation on segmentation, but it's a very essential task, right? You have in many short runtime, you have to conduct segmentation, but if you don't adapt these models to different noise, the segmentation may be so noisy and inaccurate. So I believe it's very interesting to discuss how can we do that for segmentation. Yeah.
Exactly, because again, Nikhil had a paper this year in ECCV, which is around segmentation and domain generalization. So
Okay.
I thought this continual test time adaptation theme could really make some difference over there because in autonomous driving or so, and actually Kota does have a part which uh, measures out how it performs in segmentation task. But it
Oh,
would be,
really? Okay.
yeah, it would be interesting to see how this generalizes on segmentation though. Interesting.
Okay.
And
Yeah.
because all this literature is fairly new, I think it's 2021, 2022, everything. How long did this paper
Yeah.
take you to work out?
Probably for 4 to 5 months. We have some initial idea. We want actually at the beginning, we didn't target our memory saving. Instead, we are interested in a small batch sizes. As we mentioned, like larger batch size is not always reasonable at the test time, right? You cannot expect to always have a large batch of data to feed into the model at the same time. Especially you want low latency on the prediction, so you don't want a large batch size. So at the beginning, we are interested in how can we make this test time adaptation more stable, using smaller batch sizes and continually adapted to different environments. So this is the beginning. So we propose the first strategy of reducing batch size with stabilized estimation. But later we noticed this scope may be a little limited. So we find that the current algorithms did not never, or they do not never consider memory consumptions. And but this problem is very critical, especially for many edge devices. In Sony, we have some extremely low memory edges, like only have like 4 MB memory or like a 16 MB memory. For this device, you cannot do on-device fine-tuning, right? So that's why we consider how can we make this algorithm more memory efficient. Yeah. So this is the dynamic changing of the idea from original test adaptation, continual time adaptation, then finally the memory efficiency. Yeah.
Yeah, I've seen quota take more than 2000 seconds for one single domain iteration for segmentation. So I can
Yeah.
understand the motivation, right? Nikhil, do
Yeah,
you want to?
yeah. Hi, Junyuan. Yeah, I wanted to ask you a question
Hi.
that so you have tried to reduce the number of parameters to update. Have you tried to explore how to reduce number of samples? Can we have a criteria to reduce the number of samples to?
Okay, you mean EITA and algorithm, right?
Sorry.
You mean the difference between the EITA and our algorithm in terms of reducing the number of samples?
Yeah, number of samples. Yeah.
Yeah. I believe EITA, both EITA and our algorithm can reduce the number of samples, but the difference is that we directly reduce the batch size before we feed this data into the network. But EITA requires you to first input all the samples in this batch into the network. Then they will know which one should be back-propagated. So this is quite different. EITA, so far EITA, you need to cache some data before you can do backpropagation, which means you have to do the inference to do the backpropagation of all the data at a time. Yeah.
Yeah. So one more question I had
That's
is
why
that
yeah. Sorry. Go ahead.
Yeah, please go ahead. Yeah.
Oh, I mean, yeah, you can see that this is what we measure the memory consumption of EITA. It does not actually reduce the memory compared to its baseline like a tent. Both of them have similar optimization algorithms, but even though EITA only backpropagate, you can see that it will backpropagate less number of samples in on average, like a 0.5 56 compared to the 1 in the tent, and it still consume a lot of memory. Yeah.
Yeah. One more question I had is that recently there is a CVPR paper called Echo TTA. Have you come across
Quota, right? Yeah.
No,
We
not
compare this
quota?
algorithm.
Not quota. There is a paper called Echo TTA in CVPR 2023.
Oh, I don't know which that one. Could you send it to me? I'm
yeah,
not sure.
I think that came after this work, Nikhil.
Yeah, but that is also trying to reduce the memory and the
Oh, I know. Oh, it's yeah.
meta network.
It's a new paper on CPR. Yeah, I remember that one. Yeah, I know that paper. I have not read that through. So yeah, definitely. I think we have tried to address similar problems, but I remember we have totally different algorithms. Yeah.
Yeah.
So what's the question regarding
So
that
they
paper?
try to plug some extra layers into the network. You are trying to reduce the. So instead of updating entire network, they try to update only the networks which they plug into the pre-trained model. They add extra layers and they adapt only these extra layers to.
Oh, that's an interesting idea. Yeah. I believe that's still also possible, but and we want to directly modify the currently most advanced method EIT and TENT, which has a specific advantage in terms of computation efficiency. So that's why we base our algorithm on EIT. So I believe only updating the last step could be a good idea, but it's probably I'm not sure, but it probably cannot generate to very deep networks because it probably only rely on the last layer feature. But our algorithm can adjust the memory and the distribution in each vectorization layers. So probably I have not checked layer results, but probably our algorithm could be more accurate, more accurate in the inference. Yeah.
Yeah.
Interesting. Okay. Okay, so I think that's it for the questions. Thank you for presenting the doc. The paper is fairly new, and we were glad to host you and understand how you have compared all these methods with each other on a very practical application basis, that is deploying it to devices. So, yeah, thank you so much for giving the talk.
Yeah. Also, very thank you for inviting me here. So very pleasant discussion here. So okay, I will stop sharing. Thank you. Yeah.
Thank you.
Thank you, John.
Yeah,
Have a great weekend. I'll be sharing the doc soon on.
Yeah, sure. Thank you. Have a good day. Bye.